Swayam Prabha. Digital India. Educated India.
Well, I myself, Professor Narasimha Murthy, short Murthy, NN Murthy, because there are too many Murthys in the campus. So NN Murthy is something that you can easily identify me in the internet also. So I am in the Department of Chemistry. I teach inorganic chemistry, spectroscopy, and also do some research on those fields. Bioinorganic chemistry, it's inorganic chemistry, but something related to biology, mimicking the biomolecules is that is what is the teaching and research emphasis. Generally, I do. I teach BTech classes, first year engineering students, and then we have masters. Like you are all first year MSc students, right? So we also have first year and second year. So sometimes I teach first year, sometimes I teach second year. Whenever I am not teaching BTech, I will be teaching MSc. So periodic table, when you see, normally organic chemists don't use periodic table. Only the inorganic chemists use it, because if you look at the periodic table, majority of the elements are metals. So metal chemistry it normally comes under the inorganic chemistry, right? Structure, properties, applications is what one looks at it in general, right? So we want to understand structure and bonding and properties and applications of these. So periodic table, if you look at it, you see on the you see on the left hand side you have alkaline earth metals. Then you have on the right hand side, these are called p block elements, and in the middle you have transition elements, right? Lanthanides, actinides are also there. So if you look at these, most of these are metals, and here also metals, and here also metals. So majority of the elements in the periodic table are metals, right? And then how you classify organic and inorganic or physical chemistry or analytical chemistry? Organic chemistry is in general compounds of carbon. It doesn't mean that other elements are not present, other elements are also will be present, but majority of the properties that you want to understand is based on the carbon, right? Whereas the inorganic chemistry is mostly based on the transition metals or alkali or alkaline metals, or sometimes p block elements, silicon, aluminum, nitrogen containing compounds, graphite, many of these alloys of carbon. Similarly, you have silicon, phosphorus, sulfur, and all this. Here you have some of them are metals and semi metals, right? And in general, in chemistry, most of the time people study 3D metals, and then followed by probably 4D and then 5D. Do you know the reason why a lot of studies is more focused on 3D metals? Compared to 4D and 5D, why 3D metals are major focus of attention? Oh no, applications 4D and 5D also are there, right? Okay, any other reason? Huh? Other metals also have oxidation states. Huh? Radioactive, very few. Who said that? Right. They are readily available. They are called earth abundant metals. That means in the earth crust you will find them easily. The others also you find, but they are very rare. For example, 4D. Here, if you look at platinum, palladium, rhodium, ruthenium, osmium, gold, silver, these are, they have many applications, but they are not abundant, very costly. So that means, industrially, if you want to isolate them, it costs a lot of money. So you don't, easily get them, except probably gold. But most of these metals for 3D, they are readily available in the earth crust. So they are called earth abundant. That means a lot of them are available. Okay. So that is one of the reason why chemistry of the inorganic chemistry mostly focused on 3D metals. Of course, if you understand 3D metals, you probably be able to understand, but there are differences, also similarities among the 4D and 5D. Okay. So now when I said structure, bonding and properties, that means we want to know what are the kinds of compounds apart from the broader classification of organic, inorganic and physical aspects, because you try to understand the structure, bonding and properties of these compounds using physical methods. So that is where the physical chemistry comes into picture, their characterization and all that. Okay. So what are the different kinds of compound normally, whether it is organic, inorganic, what are the different kinds of compounds that you are all familiar with? How do you classify these compounds into? General classifications, covalent compounds, for example. What are the other kinds of compounds? I have given you one example. Ionic compound. Yeah, ionic compounds, covalent compounds, coordination compounds. Yeah. So these are the broader classifications, right? Ionic, covalent, and then coordination, right? So ionic compounds are formed between what elements? Huh? Huh? Within methyl and ionic compounds are formed between that is good. That is it. That's what it is. Yeah. So you have on the left hand side electropositive elements, right? Sodium, alkali, alkaline metals. These are all quite electropositive. And on the right hand side, electronegative. So when these two combine, you get ionic compounds, right? So these metals easily lose electrons and become cations, and because of the high electronegativity, they easily gain electrons. So when these two combine together, one is there to give electron, other one is there to take electrons, so become ionic compounds, right? So these 1, 2, and then there are 10 of them here, right? So 12, 13, 14, 15, 16, 17, 18. That is the group 1, group 2, group 3. Generally, this is an old periodic table that has numbered 1A and 1B and all that. But currently it is 1 to 18. So you have in between 10, then you have 2 of them here, and then you have here 6 of them, right? So together, so this is the group 18, that is group 1, and in between you have 1, 2, 3, 4, 12, 13, 14, 15, 16, 17, 18. So the more electropositive elements combine with the more electronegative elements, particularly chlorine, fluorine, bromine, iodine. So they give rise to ionic compounds, right? So what kind of elements gives rise to covalent compounds? One of you have to raise your hand and tell me. It can be wrong. Instead of giving answers in group, sometimes I will not be able to understand. You raise your hand and tell me that what kind of elements give you covalent compounds. Now I told you, one of you told me that it is more electropositive and electronegative elements. When they combine together, you get ionic compounds, right? Now you tell me what kind of elements will give you covalent compounds. Huh? Difference between electronegativity. Okay. Yeah, so that means if you look at these elements here, you have boron, carbon, nitrogen. So within them, when the compounds are formed, a small difference in the electronegativity. Within those elements, when the compounds are formed, they are covalent. So basically sharing. Covalent is sharing. Ionic is one completely gives electron to another one completely receives electron. That is ionic, and this is covalent, right? So what is the other kind? One, we talked about the 3 different kinds, right? Ionic, covalent, and then coordination. So what is this coordination? Why this coordination? One of you, yeah, tell me. Why this coordination? There is huh? Okay. Okay. I'm not sure, the word why that coordination coming is what I want to understand. Whether you know, huh? Correct. But the word why that coordinate coming or coordination is coming. These are also called complexes. So that means why organic compounds molecules are called compounds, but inorganic molecules are complexes. That is something to do with the bonding. So we know the ionic compounds are very easy to understand. One gives electron, other one takes electron. So complete transfer of electron, ionic compounds, right? Covalent sharing. Whereas coordination, they did not know. The bonding they did not know. So that's why they called it complex. Because one case that ionic, one gives electron, other takes electron. Other one shares electron, covalent. But in this case, they did not know what exactly the bonding, because ionic compounds and covalent compounds have been studied a lot. Everything is known, but about the coordination compounds, it was not known. Bonding. Okay. So why it is called complex? Because they thought it is very difficult to understand. So complex. And coordination means some new name they have to give, right? Because already ionic is there, covalent is there. So that's where the coordination came. That means there is some understanding between the two. That is what it means, coordination. Right? We will understand more on that. Before I go into the coordination chemistry of transition metals, I want to know how much you know the structure bonding of simple molecules, right? All of you have studied, if you go and ask now 6th and 7th, 8th class student, they will tell you everything. They're very bright. So now, for example, if I give you write down simple molecules like water, ammonia, or carbon dioxide, or carbon monoxide. So how do I know? I can write water. I can write any way I want. So similarly, ammonia can be, but we know that water has a bent structure, right? So this one, the pyramidal. So how do we know all this? And carbon dioxide is linear. I can put bent. And which one is correct? So how do we know all this structure of this molecule? For example, if we take water, we know that it is a bent structure, not a linear, correct? So how do we know this? How people arrived at structures of these molecules? Okay. What is the hybridization for water? SP? SP2. So what is who is the first one to propose structures of these molecules making use of the valence bond electrons, right? There's a valence bond theory, VSEPR theory, Lewis dot structure, right? Valence bond theory. Then you have VSEPR theory. This is to explain the structure and bonding of simple molecules, or even I want to use it for other molecules also, but there is a limitation. Okay. So let us say I take a simple molecule like carbon monoxide. So what is the Lewis structure, and how do you arrive at? Why should it be 3 bond? Why not this one? Anything I can write, but we know that it is a. Which one of these is correct here among the 3 that I have written? Which one is correct? Carbon monoxide, let us say 1, 2. Third. How many of you said third? Okay. Why not second? But whenever we write carbon monoxide, it is written this way. I have never seen in textbook writing this way. Have you seen the textbook writing that? Then all of you say that third is correct. In fact, both are correct. See, plus and minus cancels out, it is a neutral molecule. Carbon monoxide is neutral molecule. But if you want to really understand, this is actually correct. But plus and minus is there, so there is a neutral molecule. So this is how it is represented. Why this is a minus and why this is a plus? Here on this side there is no sound. Huh? Everybody is silent, particularly in the back. So many of them. I see some voice. No voice here. Now, before I go to the quantum chemistry, I want to understand, how people have arrived at structure bonding of these simple molecules, and some of these molecules that we will be using in coordination chemistry. So, basically valence electrons. So, carbon has how many valence electrons? 4 valence electrons. And then oxygen? Oxygen? Oxygen 2. Atomic number of carbon is 6, right? 1s2, 2s2, 2p2. So, 4 valence electrons, right? So, similarly, oxygen has 8. So, 1s2, 2s2, 2p4. So, there are 6 valence electrons, correct? So, totally 4 plus 6 will give you 10 valence electrons. So, now we have to account for all the 10 valence electrons, correct? So, now each bond accounts for how many electrons? 2 electrons. So, how many bonds are there here? So, there are 6 electrons here, 2 here and 2 here. So, total makes it 10, correct? So, that accounts for the, but if I put only 2 bonds, then it will not account. But then the extra electrons I can put it on carbon and oxygen, but then it will not satisfy what it has to satisfy, that see, molecules containing total 2 electrons, 2, 8, 18, 2n square, okay. So, n is equal to 1, so that correspond to n is equal to 1. So, when n is equal to 2, so n is 1, 2, 3, then for 4, how much it will be? Correct? Yeah. So, which is an example of a molecule containing only 2 electrons? Huh? Huh? Helium. Helium is a molecule. We are talking about molecules, right? Right. Talking about molecules, right? So, hydrogen. So, we write only one bond. We don't write 2 bonds. It has only 2 electrons, isn't it? Hydrogen gives 1 valence electron, other gives another valence electron. So, together 2. So, together this bond refers to 2 electrons. So, that means this one, this is what is sharing. That hydrogen is happy with 2 electrons, other hydrogen also is happy with. So, one hydrogen takes electron from the other one takes electron from the first one. So, this is what is sharing. So, these are all covalent compounds, right? So, that means we accounted for molecules that are stable containing n is equal to 1. So, that hydrogen belongs to this. So, and similarly, the next one, any other molecules other than hydrogen will satisfy. For example, here you take here the carbon monoxide that I have written. So, together it is 6 electrons and then 2 electrons on the carbon. So, makes it 8. So, carbon is happy because it has 8 electrons. Similarly, oxygen again 6 electrons plus 2 electrons, 8 electrons. So, oxygen is also happy. So, these are all called octet structure, okay. So, 2 octa means 8 actually, 18 electron rule, that I do not know how many of you have studied organometallics, and in organometal chemistry only this 18 electron 16 electron, valence electron comes into picture. Organometallics we have already studied. Maybe introduction to organometallic chemistry would have studied, right? That's where the 18 electron rule and then 16 electron rule comes. There are violations to that 18 electron rule. There are molecules containing 16 valence electrons, they are also stable, but generally majority are stable because of the 18 valence electrons. So that is the third category. So we are talking about now the second category, which is having 8 electrons. So here I already showed you carbon monoxide. So this includes valence bond theory. VSEP, the Lewis dot structure is the dots you put, instead of putting the bond, you put a dot, and again it that if it is satisfying this rule, having valence electrons 2, 8, 18 and 32, those molecules are very stable, right? And organometallic compounds you would have come across. The example is nickel tetracarbonyl. Right, that has 18 valence electrons. Valence electron coming from nickel, and then each carbon monoxide gives a pair of electron. So put together 18 valence electron, and that is one of the stable molecules. And all other molecules are very stable, containing 18. Those who are not, they are not very stable. So clearly indicating that these rules, because of the valence electrons, if they satisfy, so 2n square is something easy to remember, where n is equal to 1, 2, 3, 4. So n is equal to 1 correspond to hydrogen, n is equal to 2 any other elements, particularly p block elements, and then these 3 correspond to transition metals, and then you have lanthanides, actinides and all that, right, f block elements. So very easy to find out from these equations if they satisfy those molecules, but there are many other exceptions which are also stable, but majority follow this rule. Okay. So like I told you that how do you put a negative charge here, not a positive charge, or how do you put a positive charge on this, not negative charge? How do you do that? Carbon monoxide, I said this actually is correct, but because positive negative gets cancelled out, it is a neutral molecule, and that's how it is written here. Okay, but there is a charge on this, charge on this, charge on the carbon is negative, charge on the oxygen is positive. Some of these things you would have studied, actually you would have forgotten. So it's better to read. Basics, fundamentals are very, very important. If you know it, you will really enjoy reading, and you like to do any subject for that matter. If you know the foundations of these subjects, you will really enjoy it. Otherwise, no interest. Casually go to class, take some notes, come back during the exam time. Oh, let us see what teacher has done. Then whatever you remember, you will write, and accordingly the teacher will give you marks. Some gets S grade, some gets E grade, right? Everybody has to get S grade, everybody has to get A grade, isn't it? That depends on your interest. If you don't understand, you should ask teachers. But if your teacher doesn't give you answer, you have to find out. Nowadays, internet, everything is available. Right and wrong is available, but you should know how to get the right one. Okay. So, how do you put negative charge on the carbon? Huh? One of you tell me. Huh? Tell me, whatever you are speaking, you tell me. Very good. Correct. Yeah. So there is an extra electron here because I am talking about only carbon. So I have to take the only 3 electrons. One full bond has 2 electrons, but other 3 electrons are shared by the oxygen. So I have to look at 1 electron here, 1, 2, 3 plus 2 here, 5. But valency of carbon is only 4. So it has an extra 1 electron. So that is how it becomes negative. And here similarly 1, 2, 3, 4, 5, but actually oxygen is 6. So there is a shortage of 1 electron. So it becomes plus. So that's how it is written, right? So otherwise it is a neutral molecule. So similarly, you can write down for nitric oxide. How do you write, the Lewis dot structure for all these? So some of these things, so same VSEPR theory, if you go to this valence shell electron pair repulsion theory, that you will be able to explain the ammonia is not a planar molecule, but instead it is a pyramidal molecule. Pyramidal, that means 3 hydrogens are facing down and 1 lone pair is facing up, and the lone pair bond pair interaction is what is VSEPR theory talks about. Bond pair, lone pair, lone pair, bond pair, lone pair. These are the interactions that VSEPR theory, valence shell electron pair repulsion theory. Repulsion is there, right? So that means the lone pair takes more space. It occupies more space. So when it occupies more space, this space is pushing the hydrogens below. So hence this angle, what you expect in a normal tetrahedral geometry, 109.8 something, right? So that becomes smaller. Depending on how many lone pairs are there, more lone pairs, more pushed. They are pushing because they are occupying, lone pair occupying more space than the bond pair. So bond pair means it is here. This one, one electron and one electron together is what we write as a bond. So that also, that also has a space, but that space, occupied by the bond pair is less than the lone pair. So lone pair occupies more space, so it try to pushes the bonds. Hence the angle comes down. That's how we know the structure of this ammonia. Similarly, water has 2 lone pairs, so more angle is decreased compared to ammonia. So that's how VSEPR theory. So these are all some of the theories. And the valence bond theory, the hybridization, and is all talked about, sp3, sp2, sp, sp3d2, all that we talked about, people talk about to explain the structure you want to understand. So now, by looking at the VSEPR theory, people predict what are the angle possible, what is the structure that it is possible, and all that people know, right? Valence bond theory, is again it will it only, you can say, hybridization happens, but what compound will give you what kind of hybridization, particularly when it comes to transition metals, you will not know. So it doesn't explain. That's why there is a shortcoming in valence bond theory. That's where the next the theory is crystal field theory. Most of these theory explains for molecules containing simple molecules from the p block, but when it comes to molecules containing metal and the ligand, which is what is the coordination chemistry, it will not explain. So new theory is crystal field theory. Okay, so we will look at we have to look at similarly what kind of geometries they have, whether they are linear, planar, what are the different kinds of geometries that are possible for metal compound. The same is true here. We wrote here carbon dioxide is linear, right? So same way, if you find out the number of valence electron, if you add up for 2 oxygen and 1 carbon, total valence electron you see, according to VSEPR theory, if you go, then you will find there will not be any lone pairs. So hence it will be a linear. Only when there is a lone pair which occupies the more space, then it changes the angle. But when there are no lone pairs, what is expected, for example, if there was no lone pair here, it would have been planar structure. So which is, for example, BF3, if you take, it is a planar structure, right? Based on all these theories only. So let us, move on to something, some wet cloth somebody can give. I can erase it, otherwise it's not going easily. Somebody can give a wet cloth so that I can clean the board. Anybody is there in the back? Nobody is there? So called transition metal chemistry, because from ionic covalent there is a transition in bonding. So that's why it is also called transition metal chemistry. Transition means there is a change. People knew only ionic and covalent. Now all of a sudden new compounds have formed. So to explain the structure bonding, they gave all these numbers, complex, because they thought it is very difficult to understand. Transition, because ionic covalent is a new bonding. So that's why it's called transition metal chemistry or coordination chemistry. Okay. So coordination compounds are formed by the these transition elements, particularly 3D, 4D and 5D, and others, actinides, lanthanides also they form, but there are little different kind. So let us look at the the coordination chemistry of the transition metals. So easier to understand 3D, and then we will move on to the 4D and 5D, right? But before that, what we want to know, what are the different oxidation states of these metals, right? If you take scandium to all the way to zinc, there are 10 elements, 3D elements, right? So it starts with 3D 1, goes on up to 3D 10 here. So 4s2 is also there. So that means 3D 1 4s2. So that means maximum electron that you can remove from this is 3. So hence these elements generally give +3 oxidation state. So oxidation state is important, because only in organometallic chemistry we talk about oxidation state of 0. So they are not classical coordination compounds. Organometallic compounds are not classical coordination compounds. Classical coordination compounds, which is something that has been studied since 1900. 1950 onwards only organometallic came. So it's a non-classical coordination compound. Why I call it classical and non-classical? Classical means mostly these are all done in aqueous medium, protic solvents. But organometallic compounds are not done in aqueous medium, non-aqueous medium. So that is the one big difference, right? And most of the chemistry that are studied in classical coordination chemistry are the stable oxidation state. So one example I gave you here is scandium, yttrium and all that they form because 3D1 4s2. So 3 electrons you can remove and form a +3. So scandium 3, yttrium 3 and all that very common oxidation state. +3 oxidation state is common for that is why that 3 is here. Okay. So similarly titanium, the +4 is very common stable oxidation state. Sometimes people do study other +3 and +2, but they are not stable. Okay. So when I say classical, these are the ones that are very stable, and particularly the chemistry is done in water or an aqueous protic solvent. Can be ethanol, methanol, right? They all contain hydrogen. So titanium, +4. Similarly, zirconium and hafnium. Similarly, so vanadium +5. See, you can see here vanadium. That is in the that is one other advantage of this grouping. So +5, but there are other +3 also is known, but the most stable is +5. So similarly chromium, what are the stable oxidation state for chromium? Stable oxidation state for chromium? Anyone of you here? Tell me whatever you want to tell. Can be wrong. Huh? +6. Okay. Okay. +2. You can tell loudly, no? I can hear. But I want others also to hear. You can be wrong. +3. Okay. Plus 3 and plus 6 is very common. For chromium, dichromate, chromic oxide. So plus 6 is more common than plus 3. Of course, both oxidation states are stable, very stable. So manganese, the common oxidation state for manganese is plus 7. Okay. Okay. What else? Plus 2 and plus 5 is very common in aqueous medium. Plus 4 MnO2 is there, but it is only in the solid state. They are not very stable in solution. But in solution, plus 2 and plus 5. Right? MnCl2, 6 water, MnCl4, manganese sulfate, manganese chloride, all that. Cl2. So plus 2. Permanganate is something that all of you are familiar with, right? KMnO4, where it is manganese is in plus 7, right? Plus 7 and plus 2 are the most stable oxidation state in aqueous medium. Plus 4 MnO2 is a ore of manganese, but if you put it in solution, how do you make it solution? It has to react. If you put it in acid, then it will change to manganese 2. So manganese 4 is not stable, but in the solid state it is stable. So similarly, iron. See now in the chromium, plus 3 plus 6 is what I told you. Molybdenum does exhibit plus 5. Okay, molybdenum is known to exhibit plus 5. Tungsten plus 6 is more stable than plus 3, but they do exhibit 4 also. So the tungsten molybdenum exhibit 4 and 6. Then manganese we talked about. Technetium is radioactive, rhenium, and then iron. What are the stable oxidation state of iron? Plus 2 and plus 3 is very stable for iron. Cobalt. Cobalt plus 2 plus 2 plus 3 here. Plus 2 and plus 3 both are stable. More common is plus 2. Plus 3 is also very stable. Very easy to oxidize. Plus 2 to plus 3 if you use nitrogen containing ligands, ammonia, ethylene diamine, those kinds of ligands. So easily plus 6 forms, very stable. Nickel. So rhodium, unlike cobalt, rhodium 1, rhodium 1 and 3 is very common. So similarly, iridium 1 and 3 is very common. Something different that you would expect. Cobalt, we said plus 2. In aqueous medium, plus 2 is very stable. Of course, it gets oxidized to plus 3, that is also very stable. But rhodium and iridium, the 1 and 3 is something very common. Nickel. Nickel is plus 2. Similarly, palladium and platinum plus 2 is very common. So these are called D8 elements. So that means if you remove those 2 electrons, it will have 3D8 configuration. Okay. So 3D8 elements will have a square planar geometry. In organometallic chemistry, if you have studied, after all this lecture is over, tomorrow whatever I have done, I will ask you questions and give you question paper that and I will see how much you have understood what I am teaching, right? Yeah. Sometimes is better to note down also. Listen and note down. Okay. So nickel +2, palladium +2, and platinum also +2. So on the copper, +2 is very common. +1 also is known. +1 compounds are also not very common, but +2 is the most common. Okay. So and then silver 1, gold also 1 and 3 is very well known, and zinc, cadmium, mercury +2, right? So because those are all D10 configuration, D10 compounds with D10 configuration is very stable. So let us look at some of the different kinds of compounds that these transition metals can form. As I told you, more of these are known. Because these are also known. Compounds of these are also known, but extensive studies have been done on these 3D metals. So let us see. For example, manganese. Many different, instead of chloride, I can put sulfate or other anions, perchlorate, all that anions I can put. So if you look at this, I have written for manganese 2 different kinds of compounds, right? So one has this, basically you write the other one you write MnCl4, same way, whatever is written there, 2 minus, that means there will be, let us say, because there is an anion, I need a cation, right? Cation always comes first and then anion comes. Sodium chloride, potassium permanganate, right? So always cation comes first, anion comes second. So similarly, I did not put sodium here. I put sodium on the left hand side, correct? Because it is anionic. So like sodium chloride, you have sodium chloride. So one is cation, other one is anion. So you write first cation. So similarly, in the metal complexes also you write first cation. So potassium permanganate is another example. So for this compound, since I put only anion, so I am adding now what is the cation that can be present. It can be different kinds of cations, can be coming from one of these elements here, or one of these from here, right? So here I can keep writing for example, iron 2 minus FeCl4 1 minus, or FeCl2 6 water, or FeCl3 6 water. So I can write varieties of compounds for iron with +2 and +3 oxidation state, right? So in this case, iron is in the +3 oxidation state, and in this case is +2 and +3. So like you said, the most common oxidation state for iron is +2 and +3. So I can keep writing, and but the way that things have written are different. Here 6 water, similarly 6 water, but I have here only 4 chlorides, right? So how do I write this? I did not write 10, I did not write 9, or I did not write 1 or 3. So how do you put this many molecules around the metal? How do you do that?
SwayamPrabha, Digital India, Educated India.